small side note on the binomial distribution, the negative binomial distribution, and the binomial theorem. And we will go through some results that we need to use later on in this exercise. First, let's look at the point probabilities in the binomial distribution. We use the binomial distribution with parameters n and p to model the probability of attaining k successes in independent trials, where the probability of success in each of the trials is p. So if we look at independent trials, then the probability of attaining k successes in one particular outcome, for example, that this is a success, this is a success, and this is a success, well, that is given as the probability that three particular outcomes are successes, for example, so p to the k, and that the remaining outcomes, that the remaining experiments are failures, so 1 minus p to the n minus k. Now we can have these k successes in different types of outcomes, right? Probably sometimes these three are, or we can choose these k successes in different ways. And how many ways can we choose k successes out of n trials? Well, we can choose them in choose k different ways. So in order to understand this properly, we actually need to take a look at the thing that is called a binomial coefficient. So let's just write up the definition of a binomial coefficient here. Well, for the binomial coefficient, where n is some non-negative integer and k is some non-negative integer, we say that n choose k is given as such. Well, it is the number of ways that we can choose k elements out of n elements, disregarding the order. So when we have n elements, let's say we have n elements here, then the first element that we choose, we can choose to place it in different places, right? So we have n choices. Then the next element has n minus 1 different spaces that we can place it on because the first space is already taken. And then the second element, no, sorry, that was the first element. The second element, the third element can be placed on n minus 2 different places, and so on and so on. So how long do we continue this? Well, we have to place k elements, right? So we continue this until n, until n plus 1 minus k, or we can also write n minus k plus 1. Because if I continue this all the way down to n minus k, then I have taken k plus 1 elements. So I continue it to n minus k plus 1, and I have chosen k elements. And now the thing is that if I choose k elements as such, and I say I chose this one first, chose this one second, and I chose this one third, then there might be another person who had also chosen k elements, but chose this one as the second, chose this one as the first, and chose this one as the third. When we talk about the number of ways we can choose k elements out of n in the binomial coefficient, we disregard the order. So we count both of these two ways of choosing as the same way. So we have to look here and say, well, we have actually counted too many different ways to choose k. How do we remove the regard for the order? Well, how many different ways are there to order a sample with k elements? The first element can be placed in 1 out of k places, the second can be placed in 1 out of k minus 1 places, and so on and so on, and the last element can be only placed in one space. So this is n multiplied by n minus 1 all the way down to n minus k plus 1. So there are k terms in the numerator divided by k factorial. So this is the binomial coefficient in the case where n and k are both non-negative integer. However, what happens if if n was not a non-negative integer? What happens if n is just a real number? The funny thing here is that we have actually done a kind of generalization for this. I don't know if you've learned about this on any of the other courses, but there is a generalization of the binomial coefficient that says that if r is just any real number and k is a non-negative integer, then we define rk, r choose k, in exactly more or less the same way as this thing up here is written. It's defined as r multiplied by r minus 1, and so on and so on, r minus k plus 1 divided by k factorial. And the funny thing is that by defining the binomial coefficient in general in this way, then a lot of the nice results that we have, they are still preserved. One of the things that we notice in the uh, non-negative integer case is that if I have k greater than n, then this number should be 0. For example, something like 2 choose 4 is equal to 0 because there is no way I can pick 4 elements out of 2. Now, if I calculate 2 choose 4 using this formula, this completely general formula, then what I get is 2 multiplied by 2 minus 1 multiplied by 2 minus 2 multiplied by 2 minus 3 multiplied by 2 minus 4 plus. Okay, and that was the last one. So we have 4 terms up here divided by 4 factorial. And this gives me, interestingly enough, 0 as well, since the 2 minus 2 up here just cancels, right? So the formula makes sense in a lot of different ways. And in particular, the surprising result is that it also makes sense when we apply it to the binomial theorem. So just before we continue, I'll just write up the general binomial coefficient formula here so that we can use it later. So R is real and k is non-negative integer, then r choose k is equal to r multiplied by r minus 1 multiplied by r minus let's just say multiplied by r minus 1, and so on until r minus k plus 1. So there are k terms in the numerator, and then I divide by k factorial. And, oh yeah, what was I saying? Yes, the funny thing is that this also applies to the, this also can be used inside the binomial theorem. So the general binomial theorem states that if I want to consider a plus b to some power r, then that is the same as looking at the sum for k going from 0 to infinity of r choose k multiplied by b to the k multiplied by a to the r minus k. Now this holds in general, this holds normally just for natural numbers r. Like r has to be 1, 2, 3, 4, 5, 6 normally. However, when we define the general binomial coefficient as such, this also holds for real numbers R. And that is in some way particularly interesting because that means R can be uh, anything, right? It can be negative, it can be positive, it can be whatever. And that is pretty damn awesome. So uh, I'll just write also if R is smaller than 0. Wow. Okay. So that was just a very quick note about the binomial coefficients and the binomial theorem, which we will be using later on in the proofs regarding, in particular, the negative binomial distribution. One last thing before we stop this. Have you guys ever wondered why the negative binomial distribution is called the negative binomial distribution? Because there's nothing really negative about it. It seems to be quite positive. Um, the reason why it's called the negative binomial distribution is because of this. Look at the binomial coefficient we have in the negative binomial distribution. It's v plus k minus 1 choose k. In the case where v is just some natural number, uh, we say that we use this distribution to model the probability that we attain k failures before we have attained v successes. Uh, However, when v is just some positive number, then this is more general than that. It's harder to interpret, but then we kind of think of the negative binomial distribution as just uh, almost like a more general version of the Poisson distribution, where we can have a discrete distribution where the variance is greater than the mean, as opposed to the Poisson distribution where they have to be equal. Okay, so why is the negative binomial distribution called the negative binomial distribution? Well, let's look at this thing here. By definition of the general binomial coefficient, this is defined as v plus k minus 1 multiplied by v plus k minus 2, and so on until we reach the kth term, which is v plus k minus 1 plus 1. So that is just v. And what is the next thing we can do here? Well, one thing that we can notice is that there are k terms up here, right? The first term, the second term, the third term, and so on, and we're counting down. If we minus, if we multiply each of these terms, by minus 1, what happens? Well, we can say the first term here, v, let's take that and multiply it by minus 1. And also let's take, so let's take that and multiply that by minus 1. And let's also take a minus 1 out here. Okay, and then let's try to count upwards from minus v and k terms up. Then we have minus v, and then we have minus v. What do we have? Minus v, minus v. No, wait, we don't count upwards. We have to count downwards. Yeah, we still have to count downwards. So it's minus v minus 1, and we'll also have to multiply this by minus 1, and so on until we reach the last one, which is minus v minus k plus 1 multiplied by minus 1. So it's kind of this backwards way of counting. So if we consider the axis here, and this is So if we considered the number axis and this is 0, then what we did earlier was to go from v plus k minus 1 and then so on down to v. What we're doing now is we're taking minus v and going so on down to v minus v minus k plus 1. So it's still the same number of terms, and we still multiply the same values with each other, just multiplied by minus 1. And so we multiply each of them again by minus 1 in order to attain the same value as we have up here. So all of this divided by k factorial. Now, let's notice that this has, well, the values minus 1 how many times? K times, right? Because there are k terms. So we have minus 1 to the k. And then what do we have? Then we have minus v, and then minus v minus 1, and so on, up until down until minus k plus 1. So we have k terms where I have some value minus v, where I subtract one more for each term. And that is just, by definition, the binomial coefficient for minus v. And this is why this distribution is called the negative binomial distribution, because the binomial coefficient that's inside the negative binomial distribution is in fact a negative binomial coefficient, or we can write it this way anyways. So we'll also write this down because this will also be a useful result for later. So v plus k minus 1 choose k can be written as minus 1 to the k multiplied by minus v choose k. Okay, I think that was enough for now. I'll see you guys in the next videos where we will start solving this entire exercise.